Hello everybody, it's been a while since I did a video. This is yet another Pi Day related video. We just had March the 14th and we had a lot of fun with our children here in Starkville. You can see the description link for what kind of things that we did here. Anyways, so what I wanted to tell in this video is another way of getting Viète's approximation, but this time only using triangle similarities and some algebra to get some recursions and standard Pythagoras. Nothing more, nothing less. So by no means this is in any way a new result or so. It's just old wine in new bottle. Let me say it like that. Okay. So the idea is to keep repeatedly approximating the circumference using inscribed polygons and regular polygons, obviously. The first obvious answer essentially is to use a square. So the first step is to use a square, and let me assume that the circle has a radius of 1, which means that the circumference of the circle in blue here is 2 pi. Now the closest approximation essentially is the perimeter of this particular red square. Whenever I do a polygon, I'm going to assume that the side length of the polygon essentially is 2 times of some p1, p2 and so on. This is a square, it's my first approximation, so I'm going to call this side length as 2 times of p1. Okay. Clearly, the next question will be to do it with an octagon, and for the octagon, I'm going to call that side length in green, which is here. I'm going to call this side length as 2 times of p2. You can obviously understand why I'm doing this 2 times, because I'm going to use this 1/2 as p1 here and p1 here. Otherwise, we'll have to do p1 divided by 2 and so on. It's just messy that way. So this is a little cleaner for a lot of discussion part. Okay, so let's go back. What is going to be the perimeter? It's very clearly 4 times of 2p1, which is equal to 8 times p1. What is 2 times of p1 here? The radius is 1, which means this 2p1 is root 2, which means p1 is 1 over root 2, right? So we have the first approximation to be equal to 8 times 1 over root 2. Or if I rewrite this a little better, I get 2 times of root 2 divided by 4 should be equal to 2 by pi. Correct? So if I cancel this off, what I get is what we started off. This is our first term only approximation to the Viète formula. So that's basically where we stand at the first point. So if you see this approximation formula, this is the first approximation we got. Then the next step, we'll try to get this product form, and the next step, we'll try to get the triple product, and then we'll conclude by getting a general formula as a recursion here. So that's the agenda of the video. All right, let's continue. Step 2, we're here to prove that if we have this octagon, the perimeter from the octagon will be a little bit more closer. So we have to get the first two terms, which are written on the top as root 2 by 2, and then there is a square root of 2 plus root 2 divided by 2. That's what we are aiming for. So to do that, as I told you, I'm going to assume that this red square, which I had the last time, it was drawn with in a 90-degree rotated fashion. Sorry, 45-degree rotated fashion. This is convenient because if I can now make a small construction here, I'm going to build one line from the center of the circle to one corner, and I'm going to give some names here. These names are going to be consistent throughout the rest of the video, so you can mark these. I'll call this point as E, and this AEB is such that AE equals EB, and this will be a right angle, and so is, oh my god, did I make too many A's here? So silly of me. Sorry, I meant to have ABC. Yeah, smart of me in some sense. So now the only point that everybody has to observe here is if I call the angle EOC with an orange, and in triangle OEC I'm going to call this angle in blue. Look at triangle ABC, right? So if I look at this triangle ABC and this triangle OEC, we see that the right angles are equivalent. There's a right angle pair. This is the common angle between the two. So that basically tells you that this angle BAC here should be the same as this orange angle EOC. So you have a classic triangle similarity. So let's try and build the table for the two similarities now. So this is how we usually teach. I'm going to mark the three angles here. There's an orange angle, there's a red angle, and there is the right angle. And now let's build the two triangles. The two triangles of interest are ABC and OEC. First, let's mark the corresponding side lengths. In OEC, opposite to the orange angle here, I'll have P2. For the right angle, I'll have it as the radius, which is 1. In ABC, again opposite to the orange angle is 1 minus of OB, or just make it as BC, which is 1 minus OB. I'll come to this in a minute. And then opposite to the right angle is 2 times of P2. I don't need the blue angle actually. So this is all the interpretation I need. So from here, let's do the ratios to get what is the equivalence. If I want BC, right, BC is equal to OC minus OB, but OC is 1, right, always the radius. And what is OB? OB can basically be written from the OAB right angle triangle as equal to 1 minus of square root of 1 minus P1 square. So now you understand why I had used the P1s as is and the 2 times of P2, 2 times of P1 for the side lengths. This was the purpose. So from this, what do we have? We have a nice relationship that I have using BC by P2 equals 2P2 by 1. I have 2 times of P2 square should be equal to 1 minus of root of 1 minus P1 square. So far we are in good shape. Now let's simplify this a little bit. We had derived that P1 was equal to 1 over root 2, right? So we had used P1 equals 1 over root 2. So 1 minus of P1 square under root will be under root of 1 minus 1 half, which is 1 over root 2. So 1 minus of root of 1 minus P1 square becomes 1 minus 1 over root 2. Let me make this radical a little bit cleaner. So I'm going to call this as root 2 minus 1 divided by root 2. This is a step which you must have obviously guessed by now. So multiply and divide by the conjugates to get a square minus b square in the numerator becomes 1. And the denominator, if I multiply the root 2 inside, it just becomes 1 by 2 plus root 2. Fair? So what do I have from the previous page? I have 2 times of P2 square is equal to 1 minus the root of 1 minus P1 square, which equals P2 square should be equal to 1 by 2 times of 2 plus root 2. Yeah, so that's because of the fact that I have used this term here from here, and P2 square remains the same. So from here, what can we do? We can go back and try and identify what is 2 times of pi, right? What is 2 times of pi according to the octagon? 2 times of pi. So I need some space. So let me just use the space. This much is more than sufficient to finish this off. So 2 pi here is equal to, this is an octagon, right? So 8 times of 2p2. So equivalently, I have 2 by pi is the same as 2 by 8 of P2, right? So I have P2 square is 1 over 2 times of 2 plus root 2. So this becomes root 2 times root of 2 plus root 2 divided by 4. This 4 I'm going to split it as 2 times 2. So that gives you the second approximation. Let's check if this is what we were after. If you see all the way on the top, this is exactly what is the starting point of where we wanted to head. We wanted to get 2 by pi to be the product of the first two terms. So that's where we are. All right. So now let's go plow through and let's try to look at the third step. The third step is not hard. It's again just plain algebra. We'll draw the same two triangles here, and that kind of will close this picture. So again, as you would have observed, I have rotated the octagon again so that there is this straight line here. And if you're not able to see that green color in the middle, I apologize, but it's definitely there. So now let's make some angle measurements as earlier. First, let's mark the 3 points. I'm going to call this as O, A, B, C, and this point here was E. Yeah. And I'm going to mark the same 3 angles. I called this angle with the blue. I called this angle in orange. And then there was the right angle in the middle, right? So I'm going to say that the right angle is there and there's a right angle there. And let's mark the side lengths. This side length here in red is P2. And the side length in green is 2 times of P3. Yeah, so all this is just boilerplate standard. If I repeat the picture from here, you will again get BC divided, instead of P2, you will have P3. And now BC, instead of 1 minus of root of 1 minus P1 square, you will have it as 1 minus the root of 1 minus P2 square. So it's going to be almost an identical story. So from here, what you will get would be something like 2 times of P3 square should be equal to 1 minus of root of 1 minus of P2 square. And we just got P2 square is of the form 1 by 2 times of 2 plus root 2, correct? So that's where we were, 2 times of 2 plus root 2. That's what was the previous pitch. So let's now try and expand this out to find out what is 2 times of P3 square. And once we get that, then we'll first approximate what is the circumference of the circle by using the formula that 2 pi now will be approximately equal to. So now we have a 16 gone, right? So it will be 16 times of 2p3. So this equivalently should be telling us that 2 by pi is approximately equal to 1 by 8 times of p3. And like earlier, the 1 by 8 I will split into the 2 cubed, and you will see that it will be like P3 will be written in 3 parts. So let's go ahead and solve for that step. So we had P2 square equals 1 by 2 times of 2 plus square root 2. 1 minus of P2 square will be equal to 1 minus of 1 over, I'm going to call this as 4 plus root 2. This will give me 3 plus 2 root 2 divided by 4 plus 2 root 2. Now I am going to multiply and divide by the conjugate of the denominator. So 4 minus of 2 root 2 divided by 4 minus of 2 root 2. What does this give me? The numerator will become 12 plus 8 root 2 minus 6 root 2 minus 8 divided by, here it is 16 minus 8. So this becomes 12 minus 8 is 4. 4 plus 2 root 2 divided by 8. Okay. So if I write this out a little cleaner, in a slightly not so dirty way, um, take 2 out. So I'm going to write this root of 1 minus p2 square should be written as 2 plus root 2 divided by 4 under root, which means 1 minus of 1 minus p2 square. Let me not write it there. Let's do 1 minus of root of 1 minus p2 square should be equal to 1 minus of root of 2 plus root 2 divided by 2. So this is where we are. Again, multiply and divide and do the same conjugate product. So this basically becomes 2 minus of root of 2 plus root 2 divided by 2 multiplied by 2 plus of root of 2 plus root 2 divided by 2 plus of root of 2 plus root 2. Yeah. So that becomes 4 minus of 2 plus root 2 divided by 2 into 2 plus root of 2 plus root 2. This is the first step. This becomes 2 minus of root 2 divided by 2 times 2 plus root of 2 plus root 2. One more plus conjugate multiplication, you will basically get the 2 on the numerator because you will have a 4 minus 2, and you will have a denominator to be 2 plus root of 2 plus root 2, which is the term from here, and the other product will be a 2 plus root 2. So this is where we have, and at this point we are done. So what do we have? We have 2 times of p3 square equals this term, which means p3 square will be equal to 1 by 2 times 1 by 2 plus root 2 times 1 by 2 plus square root of 2 plus root 2. So that basically cleans up the act to say that if you have p3 square, you're going to have a product of 3 terms. Each one of them will uh, one after the others. What is that word? Okay, successively add another root 2 term inside that square root. So that's how we are going to play this. So let's just close the circle in 1 minute. So what did we have for P3? As we saw, the P3 square was having the 3 product terms. This is P3 square where P3 is in the numerator. So if I do a 1 over P3, what should I get? So this term here should be equal to root 2 by 2. Like I said, I'm going to split the 8 into the cube. Root of 2 plus root 2 divided by 2. And the third term is 2 plus root of 2 plus root 2 by 2. So that's the third term. So far we are all in the same page because this is exactly what we had intended to get as shown in the top. So that's what is the to show that, and that's basically what we have. Now let's go to the last piece, which is how is it that we can get a general formula for this particular setup. To get to the general formula, what I'm going to assume is a few little notations. So this page is more useful to get that notation in place. I'm going to call this first term as x1, and this term is x2, this term is x3, and so on. So clearly, what is xn? Xn is just the same as 2 plus root of xn minus 1. This is the first recursion that we are going to use. Okay, so let's try and build the story in a general form. In the general case, we'll have the same kind of triangle as earlier, and I'm going to have AB as Pn and AC as 2 times of Pn plus 1. Again, the same 3 angles, the right angle triangle will come in place, the same triangle similarity, and at the end of the day, what we have to show will be 2 times of Pn plus 1 the whole square should be equal to BC, and BC we'll be writing it as 1 minus of P1 square under root, and this is the final recursion that we're going to show. Towards this recursion, what am I going to understand? I'm going to say that x1 is equal to 2, xn is equal to 2 plus root of xn minus 1, like what I had shown in the, or chose in the previous page. And clearly from here, what do you see? P3 square can be written as 1 by x1 into x2 into x3. Like that, Pn square will be the product of 1 by x1, x2, x3 all the way up to xn, right? So the general form will be Pn square will be of the form 1 by x1 into x2 into x3 all the way up to xn, which is straightforward. So now let's do the last two steps of this particular proof. I know this has become a little longer already. Let's just belabor a little bit more, because there are some interesting observations to get here. I'll do this in two parts, okay? The first part, what I'll do is I'll try and get a way to obtain Pn only using the xn term alone. Is that possible? That's what we're going to try and understand first. So Pn earlier was 1 over x1 into x2 into all the way up to xn, right? Is it possible to write Pn only using xn? That's the first thing that we'll go over. It's very easy to see that. The moment we get that, right, then using that in the recursion for 1 minus of Pn square will become really, really easy. So at that point, you will obviously understand where we are going. So step one, let's build a little bit more into that recursion. So what did we ask? We said xn equals 2 plus the root of xn minus 1, right? So if I solve for this, what do I have? Xn minus 2 is, so square on both sides. So xn square plus 4 minus of 4xn should be equal to xn minus 1 the whole square. Do 4 minus of whatever is there on both the left hand side and right hand side. What do I get? I get 4xn minus of xn square should be equal to 4 minus, oops, sorry, there's no square here. It's just the square root goes off and then you will just get an xn minus 1. My bad. So you will just get a 4 times xn minus 1, right? So from here, what can I write? I can write 4 minus xn is the same as 4 minus of xn minus 1 divided by xn. So far we are in the same page, right? Now, if I use the same recursion, then instead of this term, I'm going to write this as equal to 4 minus of xn minus 2 divided by xn times of xn minus 1. So the xn, just like how we had an xn and an xn here, for xn minus 1, I can again expand it one step further, correct? Now, if I do the same expression one more time and so on, if I keep going, what is the final result that I'll have? I'll have something like 4 minus of x1 divided by xn times xn minus 1 and so on up to x2. That's what we'll have. Let me multiply on both sides by x1. But understand one thing. What did we say is x1? X1 was equal to 2, right? That was our initial assumption. If x1 was equal to 2, what is the numerator here? Your numerator becomes 4 minus 2 is 2. And you have a 4 divided by xn times all the way up to x1, right? But what is this 1 over xn x1 all the way up to x1? This is exactly the same as Pn square that we had, right? So from our definition of Pn square, we have 4 minus xn is the same as 4Pn square. Does that make sense? Because this term exactly was the same as 1 over P1 square, right? So we have Pn only in terms of that xn. So our first step is clean. This is a really nice setup that we have. Let's now go and look back at this recursion. So the recursion that we have to show is, I'm going to copy this recursion alone. Okay, so let's build on this recursion. So this is what we want to show, right? Let's start with the right hand side and then we'll slowly construct what is the left hand side. So the right hand side, that's what we know so far, is of the form 1 minus of Pn square. First, the smallest term here. But from the previous page, what did we have Pn square as? This becomes 1 minus of, 1 minus of 4 minus xn divided by 4, which is exactly the same as xn by 4. So if I take the square root on both sides, I get this is root of xn by 2, right? Sorry, I thought I was writing on the previous page. So all I did was to take the square root of 1 minus pn square, the right hand square, the inner term is as shown. And what do I have as 1 minus of pn square? This will be 1 minus of by 2, which can be written as 2 minus root xn divided by 2. By this point, you should know this like the back of your hand. Product form, this becomes 4 minus xn divided by 2 plus root of xn. We are done, because look carefully. What is 4 minus xn? 4 minus xn we just saw was equal to 4 times of pn square, correct? And what is 2 plus xn? This is xn plus 1. Fair? Oh, there's a 2 here as well. So there's a multiplying factor of 2 times of this. So you'll only have a, so right. But what is pn square? Pn square is the same as 1 by x1, x2 up to xn. This is pn square, right? And if I multiply by this n plus 1, then this exactly becomes pn plus 1 square. And that essentially is what is our left hand side. So we are basically done with the general result. So what did we show in this? We showed that as you keep adding the so here what did we show essentially is, instead of the 8 gone, if we went into the 16 gone, which is the third layer. The first one was a square, then the 8 gone, now the 16 gone. You have all these three terms getting to a product form. Now, if you go to the n gons, all you might have are the product of all of these n terms is what we conjectured, and that's what we had to prove. So the general result we had conjectured was that if you go to the n gon will have exactly the same recursive form from the n minus 1 1th layer gone, and we just used algebra so far. The only triangle similarity that we had to take was from our first step here. So that's about what I wanted to say. It's a cute little observation. You have other ways to see the same formula from Viète. If someone just knew a little trigonometry, you could do a cosine expansion and it comes out like clockwork. This is only to show that we don't need really sophisticated tools, and all we need are just triangle similarities and a little bit of algebra. This is more like grunt work, which is a little tedious but rewarding at the end of the day to understand some recursions as well, right? So I'll stop it at this point, and thank you for your time, and maybe I'll see you sometime when we see you.